Welcome to Maths with EJD. In this video, I'll be talking about backward induction in extensive form games. Um, you know, 3 videos before now, I started talking about extensive form games as a kind of game in which players involve themselves in some sequential decision-making process. So after that introduction in that first video on these particular extensive form games, we went ahead to talk about game trees and decision nodes, which where we saw a very nice way of representing extensive game forms. Afterwards, we talked about the sub-game perfect Nash equilibrium, where we actually saw the possibility of arriving at a perfect a kind of equilibrium, right, for each sub game in an extensive form game. So here, let's talk about backward induction. So the idea of backward induction, of course, as the name implies, we'll see that in a minute. So the definition, backward induction is a method to solve extensive form games by analyzing the game from the terminal nodes. So it's more like you analyze the problem by starting from the last node. So you're analyzing the game from the terminal nodes backward to the root. So normally, right? When drawing a game tree, you start from the root node. That's the starting point, and then you go along the branches until you get to the terminal node, where you have the final payoff for whatever actions the players involved have taken. But here, backward induction tells you to start from the terminal node and work your way back up. So it's more like go starting from the solution and starting from the this final point down to the beginning of the solution, something like that. So let's look at the steps involved here. Steps in backward induction. Okay. So the first thing is you start at the terminal node. Start at the terminal nodes and determine the best choice for the last player to move. Okay. Then the second thing is you move to the preceding decision. Move to the preceding decision node and consider the best response given the future play. All right. Then 3, repeat until reaching the root. All right. So now we'll use our usual example again. So that is the example about splitting $100 between player A and player B. So I'm going to take the pain to write it again, so we can properly get the idea. So the scenario again is this: 2 players, A and B, decide how to split $100. Okay. So player A chooses between splitting fairly, in that case, $50 for each person, or unfairly, which is $90 for A and $10 for B. So if A chooses unfairly, B can accept or reject the split. If rejected, both get $0. So already we have identified the strategies are available to player A. It can be fair or unfair. Then we have also identified the strategies acceptable available to player B to either accept or reject. So those are the things. Now, let's look at it in the context of backward induction. So now, in the case of backward induction, now we have to start from what player B will end up doing because player A plays first. And since it's backward induction, so we go to the destination and then work our way back to the beginning. So let's see that. First of all, we have player B's decision. Player B's decision. Okay. So one way to actually do this is to probably you can draw the game. Um you can draw the game tree at one corner. Uh Maybe I guess let me do that to demonstrate. So of course you have player A who can be fair or unfair. If he's fair, that's 50-50. So this is more like some rough work. B. Then if B can accept, so if B accept, that's 90-10. Then B can reject. If B rejects, that would be 0-0. Okay. So this is the scenario we are looking at all this now. Looking at this. So normally this is what the game tree should look like, right? Now, so for backward induction now, so we can talk about player B's decision. We can already start from the end, right? So this is the part where we have player B. Player B. So if player B is confronted with the choice of accepting, player B goes home with $10 and player A goes home with $90. But if player B rejects, nobody goes home with anything. Everybody gets nothing, right? So what does that tell you? For a rational person, right? A rational person will want to go home with $10 rather than go home with nothing, even though the person has been treated unfairly. So in this case, player B's decision will see that at unfair, all right, B chooses accept. B chooses accept. Okay, I guess I want to. So at unfair, right? If A is unfair, if A is unfair, B chooses accept. So B would rather accept $10 than to go home with zero. Okay. So at unfair, B chooses accept. That's the first thing. So, and that is payoff, for payoff of $10 over $0. That is commonsensical. So that's us starting from the end. Okay. Then the second thing is this. What will be player A's decision now? Player A's decision will be such that knowing knowing that B would rather go home with 10 than go home with nothing, All right. Um, what do you think player A is going to do? So knowing B will accept, okay. A prefers, A would rather prefer the best option. So for him or her, so A prefers unfair, okay. A prefers unfair and goes for 90-10 over 50-50. So here, uh, 90, so A gets $90 over 50, $90 over $50. Okay. So here now, B chooses accept, right? B chooses accept. Uh, yeah. So A would rather go for 90 over 50. So in that case, we arrive at that. So using a tree diagram, right? Using a tree diagram, that simply means that, we start from so we have player B around here. Player B is confronted with either to accept or to reject. If he accepts, that is 90-10. If he rejects, that is 0-0. So 90 out of 90-10, he gets 10 if he accepts, and he gets 0 if he rejects. All right. So for a rational human being, right, would know that he would rather accept to go home with $10 instead of reject and go home with 0. So working this back up now, what will lead to this point is the fact that B already knows that, B has two, I mean, A has two options, right? A has two options. Um, so A has two options. A can choose to be unfair, or A can choose to be fair. So if A chooses to be unfair, to be fair, they both have 50-50. All right. But since A already knows that B would rather choose 10 over 0, then he can take his chance to be unfair. And then it goes unfair. So, and this is the idea of backward induction. So at the end of the day, we have our result as 90-10, even from backward induction. So we can make a conclusion in this case, or we can state the results. The result is such that um, the result backward induction, using backward induction, the solution is number one, player A chooses unfair, and then player B chooses accept. Okay, so with this, we've come to the end of extensive games, but we have not come to the end of game theory because there are so many other things. In fact, after now, we'll begin to explore the concept of evolutionary game theory, and we see how game theory plays out in the world of biology, which also has some social implications. So, you don't want to miss any of this. That's why you want to definitely subscribe to this channel and hit the notification bell so you can always get alerted each time a new video is released. You also want to comment to let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And then you want to like and share so that more people can have access to this great, great content. Till I come your way again, keep playing the game of life with wisdom. Bye.